And welcome back. Now, as you can see, the ATTiny85 is making a reappearance this week because I've been looking at this a little bit more detail, because when we left it last time I was a little bit ambivalent and in two minds really about whether the ATTiny85 could really cut it as a microcontroller in today's market, because it's very popular. And of course there is a huge following for the ATTiny85, so I thought, right, I'm obviously haven't quite bought into it yet. What do I need to do to make this the chip of choice? I've been playing around with a few things, and I've downloaded a little sketch that makes this LED blink here. You can ignore this one down here. In fact, I'll tell you what, let's use a high-tech solution to stopping that LED blinking down there. That's the heartbeat LED, this one here, because it's plugged into the Uno, which is being used as a programmer, and that just tells us that yes, I'm communicating rather nicely with pin 9 on here, sort of a heartbeat, I'm okay type thing. So let's just use a high-tech solution and switch that off. It's called a bit of blue tack on there because it's distracting otherwise from what we're trying to do. There we are, look. Sometimes the oldest solutions are the best. Well, I can't think of any other way of switching it off because it's all hardwired, isn't it? Anyway, so there we are, high-tech blue tack to stop you looking at this LED and looking at this one instead. Now, we're going to take a hypothetical situation here, but a very real problem that comes when you're programming the ATTiny85. There's only so much code you can write, well, that Benny can write, let's be honest, before we think, this isn't working quite as I intended. I know, let's put a few debug statements in and find out what's going on. So let me show you the code that I've got here, this simple blinking on-off one. Here we are, this is the sketch, right? This is what we're actually running on the workbench at the moment to blink the little light. But I thought, okay, if I really want to find out what's going on here and when things are happening, I'd normally put in a few, serial debug type statements, as I call them, serial print statements, right? So let's just do that. Now, if you're familiar with the ATTiny85 setup, you'll be saying to me, even as I'm uncommenting out these debug statements, excuse me, Ralph, are you sure that's going to be okay? Well, let's have a look. Let's compile it. In fact, let's move this line up here so we can see some of the statements. We do get some warnings out, by the way, even when we compile this, because deep down into the AVR type code, somebody somewhere has not conformed to the standards of the current version of the compiler. For example, this name here, I think is expecting with a couple of underscores at the beginning, but we'll just ignore those. We're not really bothered about that. We're bothered about this flashing light, aren't we, down here? Oh, hang on a minute. We've got a bit of a problem. Oh, look, it's saying Serial.println. I don't know what you're talking about. In fact, it says Serial was not declared in this scope. I'm actually trying to highlight this. There we are. Serial was not declared in this scope. Well, oh, idiot that I am. Of course, there is no UART on here, is there? There is no serial as such on this chip, nor on this development board. I mean, we're using on here, remember, on the actual main board to program all this, we're using the SPI pins down here, right? Just to make it easy, and using this rather nifty little board. And that's fine to a point, except of course there's no USB socket that I can plug in anywhere. So what are we going to do? This is a bit of a problem, isn't it? I mean, okay, so the code we're using here at the minute is particularly simple, but I still want to be able to, tell me when things are done. Quite often, putting a statement in the setup like this is very good, because at least it's got through this bit. Okay, so there's no serial port chip UART to use. What are we going to do? Well, of course, there is an immediate solution, which doubtless many of you are shouting at me at this very minute if you're watching this video. And it is, of course, the software serial, which means you can use any pins of your choice, any GPIO pins of your choice on an AT whatever, in this case a Tiny85, to give you this serial output. So let's load that up and see if that works any better. Right, so here we are then. Now we've added the software serial library, and this is a pretty simple thing to do. We just add in that one there. We don't have to make any changes for it with the ATTiny85. You do have to declare though 2 pins, because there's the transmit and receive pin. Now, strictly speaking, I'm only interested at this point to receiving stuff from the ATTiny85 to my debug window, serial monitor, just to tell me what's going on. If I do want to receive stuff from a serial port, then of course, yes, I'd need 2, but well, okay, well, let's choose pin 5 then for the receive on board, because pin 5 we'll come to in just a minute why I've chosen that one, and pin 4. These are digital pins, not physical pins. Okay, so if you look at a real close-up, so we've chosen 5 and 4. So if we look at this, and I'll turn it around the right way so we can read it, and in fact even zoom in a little tiny bit on it. Is it going to do it? Yes, it is. There we are. Perfect. Right, so we're choosing pin 5, or P5 as I say, which is that top pin there, and we're choosing pin 4, P4, which is physical pin 3, which is what I've got that plugged into, as you can see. All right, and the flashing LED is in P0, this one here, which is physical pin 5 and ground. No resistor required on here. These are quite high voltage LEDs, don't need anything. Right, so that's what we're doing. Okay, right, here we are back at the code window. So we've chosen pins 5 and 4, and we've called it serial, so that we can say serial dot whatever, serial begin, serial print. Now, in the interest of saving memory, because we are quite severely restricted in memory on the ATTiny85, I've put all these strings, look, into flash memory. This is how you do it. You just say F, and then put your constant string inside it, and I've done that with just about all of them. Okay, so that brings down our memory footprint quite a bit, because after all we are including another software serial library here, which will use up quite a bit of our 8K space. In fact, if you look at this one here down here, look, where I've previously uploaded it, you can see it's using 2492 bytes. Let's just upload that then and see what we can get out. It should be exactly the same rendering of the LED down here. So let's just upload that. Compiling. Now, I've said before, it does take quite a long time to compile, don't know why, and to upload, probably because it's going through the Arduino, but there we are, it's done it now. So there we are. So the flashy LED is still flashing down here, but where's the output? Well, let's load that up next. Right, here we are. So this is a close-up of the actual monitor itself, and as you can see, look, here are all the debug statements. If you don't believe me, I'm going to actually press on here. There's a reset button, and we'll be talking about that later as well. There we are. So now it's just starting. Look, set up complete down here, and then it's constantly going through all these iterations. Now, of course, yeah, in this mock-up, our actual displays here aren't particularly interesting, but you know, this is sort of the typical thing we do, isn't it? Just to make sure that a program's got to a certain point, that the value is correct at a certain point. Great. So we're thinking, well, that's it then. Problem solved, isn't it? We can now use Serial.println in our ATTiny85s. Not quite though. Because as I said, when we look at this, we are using 2 pins, not just 1. So we're having to use 1 pin anyway, just to get the data out. Fine, that's the law of physics. You've got to connect a piece of wire to something to get the data. But we are using another one here, which is sort of a bit of a waste, isn't it, really? We'll talk about that in a sec. So let's have a look at this down here. Look, 2492 bytes, it says, which is 30% of our program. This little tiny sketch is using 30% of our program space out of the maximum of 8192 bytes. Right, that's significant, I think, isn't it, really? And not just that, we've already used in our global variable that we've used 144 bytes, which is 28% of our dynamic memory. This is SRAM. So we've only got 368 bytes left, so it's not a huge amount. I've already put the strings into flash RAM here. If I didn't, we'd be using up even more of this. It wouldn't be 144 bytes, it would be, well, 144 plus however many bytes these strings will take up. What's that? You want to see that? All right then. We'll take them out of flash RAM, and then you can see how much this changes by when we recompile it. Right, it was just those two lines actually. If you look further down here, I hadn't actually put these into flash RAM anyway, which I should have done. I mean, there's no excuse for that. But anyway, let's compile this and see what it does. So remember, it says 144 bytes there at the moment, yeah, and the program bytes shouldn't really change, 2492. Right, let's compile that then. See what it does. Oh look, so 2426, it has changed a little bit. Presumably these are being stored now in the program as well, but 186 bytes now in our dynamic memory is being used up. So we are slowly encroaching upon, you know, memory that, well, we'd rather use for programs rather than debugging and stuff we don't need, like this software serial. So first things first, always put your strings here for prints and all that into flash memory, which, as you just saw, is just by putting in the F in front and in brackets like that. Okay, so that will immediately drop this from 186 bytes, which you'll see now, to 144. So that's the little saving. Now, if only we could have this software serial and not use this pin as well, we'd be getting even more value out of this chip, wouldn't we? What we really need is a library that allows us to send but not receive. It can't be that difficult to do. Maybe I'll knock one up. Let me have a look. And lo and behold, here we are. So we've now got a send-only software serial. Now, of course, I didn't write it. I was going to, actually, I must admit, but I thought I can't be the only person in the world that wants this. So I had a look, and guess who popped up yet again? Yes, Nick Gammon from Australia, the guru of all things Arduino and C++. He'd already taken the software serial and created a send-only version of it. So good for Nick, I don't have to do anything. So instead of having software serial included, we have send-only. We now only need one pin, pin 4, and everything else pretty much the same. Yeah. Okay, well let's just put everything here. This one here, for example, should also be in flash memory, so let's put that in there as well. Right, here we are, all done and dusted. So all these strings now are in fact in flash memory, whether it's this bit or down here, just to reduce our memory footprint, because after all, that EEPROM stuff just isn't used most of the time, so you can definitely save some memory by doing this. Software serial, one pin now for send only. Right, let's compile that and see how much space that uses. Oh look, now it says Sketch uses 1610 bytes, 19% out of the 8192. That's a bit of a drop, isn't it? Compared to previously we were over 2K, 2000 bytes plus, 21 I think it was. And look at the global variables as well. 54 bytes, only 10% of your dynamic memory. That is a massive saving. So good work there by Nick Gammon, of course, for creating this send-only software serial. And the fact we've put all these strings now into flash memory as well has reduced this as much as you can reduce it by. Now, the question that should be on your lips is, great, I understand what's happening, but how do you get the data out of this chip onto the screen? Okay, let's cover that first. I've said that we're using pin here, pin 4, so we've attached something to pin 4 here. What is it exactly that we've attached, apart from a wire, I mean? How's it getting back to the computer? Can't be coming back to here because this isn't connected somehow to this, is it? What are we doing? Okay, the marvelous and friendly FTDI programmer makes a reappearance. Now, I did show how these worked. Must be a year ago or even more now. These are very cheap, very useful, and what you would normally use them for is to program stuff with these. So if you've got a Pro Micro, for example, you'd connect up all the 6 pins on here to the 6 pins equivalent on the Pro Micro, plug it in, and this then acts, this whole thing acts here pretty much the same as that USB socket does there with the CH340G chip, which you can just see through there. So that plus that is the equivalent to all this for a chip that doesn't have any of that. However, we're not using it to program anything, we're just using it to receive on this blue pin. So that's how we're receiving the data from the chip, and these other two wires are simply power. Why do I need power from here to here? Well, I don't really. I can disconnect these. So if I disconnect the power supply there, has it stopped flashing? No, it's still going, obviously, because it's powered by that USB cable over there. But let's plug this back in again just for a second, because if you remember, we had some argy-bargy when this was plugged into this board for the SPI use, which we're not using at the moment, I2C and all that. So if I now take this off, well, obviously it keeps running now because it's powered by this as well. You can see that it's quite a small little footprint now to get the stuff out. What do we do with this end here? Obviously it's not plugged into the same end as this one over here that we're programming this device with. Where does this go? Well, it just goes into the computer the same, well, into my hub anyway, but it's defined as a different USB port. So effectively I've got two USB ports assigned, one to this one here and one to this one here. And when this is plugged into here, they all join up really. Let's have a look at my ports view and you'll get a much better idea. So here we're looking at the USB COM ports on my computer. These ones down here. COM4, now COM4 is indeed the one that we're using here on the green cable, and COM7 is this one at the back that we're programming with. So my Arduino IDE programs using COM7, but my Sublime editor IDE uses COM4 to look at stuff. So if I bring that back into play, here we are. So this is the Sublime editor, and all I've said is monitor COM4, which is the output from here. Now the way you do that is by clicking on the Arduino, going down to serial port, and from that, oh, let me just get rid of that, Arduino serial port, and as you see it's picked the wrong one at the moment. We're actually on COM4 for output. This is what we're monitoring. I'm not programming. COM4, and then there's a shortcut key. It's Alt-M, Alt-R, or just go to serial monitor and run. And there it is, and that's the output from this little chip now running. So that's it, it's coming up out from here into here, all via that one single transmit wire, and it's going to the RX at this end. This is receiving it, this is sending it, and that's what you're seeing on screen. Right, okay, so that's great. We can now got a lightweight send-only serial software library, thanks to Nick Gammon, and we're using that with a single pin out of our, well, rather limited selection of pins available to us on the ATTiny85. So what else then on here could we do to make it even more useful? Well, if you remember, when we used the standard software serial, we were using P5, which on here is this top left pin. Now that top left pin is only used currently for a reset. That is, well, when you press reset. For example, when you press reset on here. Well, when you press reset on here now, after my jiggery pokery, I've made some amendments to this board, but you need the reset working, because when we program via this board here, via the SPI pins, we need the reset function to reset this chip in order for it to accept the new program. So reset has got to work. Is there any way we could say, I don't want pin 1 to be used for a reset, I'd like to use it for a standard GPIO? Wouldn't that be great? Because then you'd have, well, 6 pins that you could actually use and just 2 for power. Then this becomes even more valuable as a tiny little device. And yes, you can do that, but you would need to use a standard AVR programmer, which I haven't got, although it'd be pretty easy to buy one for about, I don't know, $5 I think they are, which plugs in pretty much the same way as we do now, and doubtless we could probably cobble something together ourselves. But the problem is that you'd have to send a command down the wire to the ATTiny85 and change one of the configured fuses, as they're called on here. There's a specific area within this chip that are, well, they're called fuses, but they're actually bit values, and once changed, it's quite difficult to unchange them. They're set in the factory to a default value, the most likely value you're going to need, and then left like that, because, well, you can change them if you want, but if I was to send down a command to say I do not want pin 1, physical pin 1, P5, to be used as my reset pin anymore. I want to use it as a standard GPI. It'll go, okay, that's great, done. And then when I try to program this again via SPI, it go, I'm having a bit of a problem here. I can't reset the chip anymore. So what a standard AVR programmer device does, and it looks pretty similar to something like this. What it does is send down a 12-volt pulse to the chip on this pin here, which flips that bit back again from a standard GPIO to a reset. Then it can program in the normal manner, and once it's finished, it says not a reset pin anymore, standard IO. And that's what it does, keeps changing it. Now, funnily enough, I'm not the first person, of course, to want to be able to do this. And if we go to my code window, you can see where somebody's actually created their own programmer to do just this. First of all, they used a 12-volt battery as part of that, but now you don't even need that. You can just do it all within the Arduino. Let's have a look at that next. So here we are at Wayne's tinkering page, as he puts it, and it's all about the ATTiny fuse reset. So what he's created here is this circuit that, well, basically allows you to reset what's on pin 1 via this command here and 12-volt battery. Except that was a bit too much hassle, I think, for most people. So he's created a Mark II of this that doesn't require that 12-volt battery. So this is his second attempt at programming it all. And what he's got here now, instead of that 12-volt supply, he's got this charge pump here with this combination of diodes and capacitors that bring the value up from 5 volts to 12 volts. That then gets blasted into pin 1 and flips that bit to say, you are no longer a GPIO, you are now a reset pin, and vice versa. So I'm going to have a closer look at this and play about with it. It might be a few weeks or months even before I progress this, because I'll also look at a standard AVR programmer. It might just be a lot less hassle at the end of the day rather than creating this, but I don't know. Let's not say never, and we'll see how we go. In the meantime, though, I am stuck with the fact that pin 1 is a reset pin. Now, I mentioned in my last ATTiny video that I was having problems with this reset pin. It didn't seem to be doing a lot, and that's because it wasn't wired up to do a reset on here. It was wired up to do a reset on here as far as I could work out. So I've changed it underneath. I've made some modifications. Basically, I've brought the reset pin to the back end of this switch, so one of these pins here, via a 330 ohm resistor, and cut this here. So this is no longer now connected to reset on here. So basically, if I press this switch when it's all plugged into this board, this reset no longer resets this board. It does in fact reset this one, because I think it's much more useful to have a reset pin on this shield, so that when I press reset, it does actually reset this chip rather than trying to reset this one, which I can do anyway, or just unplug it or something. You want to see it in action? Of course you do. Let's bring up the monitor for that one. So here's the debugging window going away quite happily, showing us what we got. And if I press the reset button here, you'll see immediately a statement coming up saying to the words like setup is complete. There we are, setup is completed. This is iteration 1. We've reset the counter and everything else. So that works now much more the way I expect it to work and want it to work. I don't really want to be able to reset my Arduino using this plug-in board. If I have to, I'll just unplug it and plug it back in, or indeed press the reset button, which is only right over here anyway, quite easy to do. Perhaps the standard Arduino, the kosher one from Italy, maybe it's laid out slightly differently, I don't know, which might make it more awkward. But for me, this works just fine. I'll place a diagram of how I've done this on the video description. So below this, where am I? There we are. Below this video, there'll be a circuit diagram of exactly the modifications I've made to this. It's literally one resistor and one cut track. Okay, so it's not different. Let me just talk you through that then. Here's our ATTiny85 with a reset pin that we want to modify. There's the actual reset pin or button on the board, and there's the incoming inputs, right? Reset, 5 volt and all that. Now currently the reset is connected to that pin with a capacitor, the other side of which of that switch goes down to ground. There's nothing connected to the ATTiny85 at all. So we want to change this so that reset button actually resets the ATTiny85. So we cut the track to the switch and connect that switch up now to the pin 1, the reset button of the ATTiny85. So when that switch is closed, it brings the Arduino's or the ATTiny85's reset pin to ground. Now I've also put a capacitor the other side of those header sockets to replace the one we've removed, but I'm not convinced that's necessary. Actually, that was for belt and braces. They're both 10 microfarads. And that is all there is to it. Simple really, isn't it? Right, so there we are then. I think that was just a little heads up on the fact how we can make the ATTiny that little bit more useful when you're programming. Actually, you do need those debug statements. I do. Well, I don't. Benny does, obviously. I don't code anything. And it just helps you do things that otherwise would be very frustrating. And also I'm going to investigate even more into that pin 1. Now don't forget that software serial only library. I'll put a link to where that is, but also put a copy under the video here again, because that really does not just give you the send only software serial, it cuts in half the amount of code that is dragged in as part of the compilation process. So I think you'll find that very useful as well. If you need that feature, and of course if you suddenly think, well, I've created my program now, I really don't need that debug statement anymore, then you can just copy it, comment it out, can't you? Have a sort of global variable where the debug is determined, so you don't try to send any, and take out the software library. Easy. Right, we're going to leave it there. I think that's enhanced my feelings about the Tiny85. I think it's become a little bit more useful now. And if I can crack that pin 1 problem, that gives me an extra pin, so that's 6 now out of the 8. And I think that would make it a surefire winner in certain circumstances. Okay, great. Hope you enjoyed this. Don't forget to share and give me a thumbs up if you think it was worthwhile. And I'll see you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.